So I have with me today Dr. John Baumgartner. And John, tell me, are you a geologist? What is your actual PhD?
It's in geophysics and space physics. And I'm primarily focused on solid Earth geophysics. That means what goes on inside the Earth and also how it affects what happens at the surface of the Earth.
Right.
But it's primarily solid Earth geophysics.
And you have done some work that I've followed in the past and just have been intrigued by. There was a whole article in U.S. News and World Report several years ago on the work that you had done. So here's a secular, popular magazine that had done an article on you. I thought that was really very impressive.
Right. The title was The Geophysics of God. And so it was of interest because I was sort of outside the normal framework by bringing God into the picture. Mm-hmm. And so it was primarily of my computer modeling of the Earth and of plate tectonics and of my belief that the flood was a tectonic catastrophe. A lot of plate tectonics unfolded during the few months of the flood, and my developing serious computer models to study that.
Why do you suppose that evolutionists just simply discount the flood? Why do they not even consider it, or am I wrong?
No, I would say the main reason is the time scale. Is the time scale that they have adopted, have assumed, and this was predicted, this is predicted in the New Testament, in the Bible, right, that in the last days there would be scoffers that would say, where is the promise of Christ coming? God just doesn't intervene in the affairs of this world. All is continued just as it was since the beginning of creation. Basically, with the advent of radioisotope dating, all opposition fell by the wayside. And so hardly anybody was willing to challenge the idea that the Earth was billions of years old after the advent of radioisotope dating.
And that's what I wanted to talk to you about then. So tell us about radioisotope dating, its advantages, disadvantages, its weaknesses. What do we need to know?
Well, because this is such a challenge to a straightforward understanding of the Bible, especially the early chapters of Genesis, it was recognized. There was a board member of the Institute for Creation Research in the 1990s, okay, Bob Armstrong, who just was adamant that we had to address this issue. So there was a group of 7 PhDs assembled in 1997 to specifically address this topic, and namely, why do these radioisotope methods give dates for rocks from millions to billions of years old when the Bible indicates the Earth is only thousands of years old? How do you account for this discrepancy? What is the source of this discrepancy? So we were charged with that task of trying to identify what assumption or what's responsible for this huge discrepancy.
Okay, and so it became known as the RAID project, which stands for, it's an acronym standing for?
Radioisotopes and the Age of the Earth.
All right, good.
So you have to use "the" in the acronym. But yeah, so we became known as RAID. It was an 8-year project. Amazingly, we were able to raise over $1 million. Most of that went for doing rock analyses.
Doing the actual science.
So we sent a lot of rocks to laboratories, professional labs that do this.
And what was your part in the project?
Okay, I headed up the carbon-14 project, but I also was very involved in some of the other projects, especially the one involving helium retention in what are called zircon crystals, a tiny mineral known as zircon. And we already knew that it had already been published in the early 80s that zircons could retain a large fraction of their of the helium produced by radioactive decay of uranium. And but no one had ever measured how fast helium leaks out of zircon, what its diffusion rate was.
All right.
So one of the major things that our rate team did was we contracted out the measurement of the helium diffusion rate in the mineral zircon.
Why is zircon important? Why isn't it something else?
Zircon is like a tiny time capsule. It's common in granites. And the minerals are tiny, about the diameter of the human hair.
I see.
They're small, but there are a lot of them. And because uranium substitutes nicely for zirconium in this zircon crystalline lattice, it's a silicate, zirconium silicate. You can substitute uranium because it has the same chemical valence and roughly the same atomic size.
Okay.
So you often get many parts per million uranium, even up to 1% uranium in these zircon crystals. On the other hand, zircon's very hard. It's not as hard as diamond, but nevertheless very hard. It also has a high melting point.
Okay.
So those crystals are durable, and even when the granite breaks down, those zircons survive, and you find them in sandstones.
Okay, all right. So let's move on. So let's really try and bring the cookies, put the cookies on the lower shelf. We want to understand helium in zircon and the release of helium.
Right.
So go ahead.
So we examined some granitic rock from a drill core in northern New Mexico into the crust.
Okay.
It went about 2.5 miles deep. So that's a pretty deep hole in solid granite.
Okay.
It was done to study hot, dry rock geothermal, the possibility of using hot rock to generate geothermal energy. But we used the rock that they took out of this hole.
Right.
All right, we analyzed it, and we found, well, the deeper you went, the hotter it got. And so the less helium, the hotter the rock, the less the helium. But you had a nice sequence. We had all that core archived at Los Alamos where I worked.
Okay.
And I had access to it, and so we were able to get samples, fresh samples of that core, and have them analyzed. And one of the things we did was is measure the diffusion rate in the zircons. We crushed the rock, extracted, in one case, 1,200 zircons from a sample, and sent them to the laboratory for analysis to see how fast the helium would leak out. If we put them under vacuum, cranked up the temperature, we could measure how much helium came out, how fast it came out, and very precisely determine what the rate of diffusion was of helium through the zircon material. We could also measure how much helium was in the zircons to start with.
All right.
And so we confirmed these earlier measurements. And
now wait a minute. How would you know how much helium was in the zircon to start with?
Basically, we heated the zircons enough to extract essentially all of it that was there. We heated it until we got no more helium out. So we allowed it pretty well to exhaust the helium in the samples that we had. So all that was there we got out, and we were able to collect it and measure it. Okay, so we could also look at how much lead. Uranium decays to lead through a series of intermediate steps.
I still got it back. All right, so you're analyzing these zircons, and obviously some amount of helium has been leaving. You're analyzing how quickly it's leaving the zircon.
How much was there?
How much was there originally?
How much was there originally? Well, we're able to measure how much lead is in these zircons, and it turns out that when these zircons form, when they crystallize, they exclude lead. So you can assume that there was no lead in the zircons to start with. You can also measure how much uranium is there. So the uranium has decayed over time into lead.
Okay, and you're getting to why this is important.
All right, the reason it's important is the diffusion rate we measured means that is so high that helium could not have been retained more than a few thousand years. And if the sample were really 1.5 billion years old, there would be almost no detectable helium today.
Because you're judging that based upon the diffusion rate.
Right. How fast it leaks through the... So we have, in effect, two clocks for these zircons.
Okay.
We've got the rate, a clock based on the rate of how fast uranium decays to lead today. As we measure it, we can measure that rate in the lab.
Mm-hmm.
We can also, there's another clock based on how fast helium leaks out of the zircon.
Okay.
And we can measure that rate today in the lab, which we did. Okay, there's a discrepancy of a factor of 250,000. The helium diffusion rate says that these zircons can be are no more than about 6,000 years old, whereas the rate based on decay of uranium to lead says that they're 1.5 billion years old. So the ratio of those two numbers, those two dates, is 250,000. So the clocks don't agree. There's a huge disagreement. So which one of the clocks, if either, is correct? Well, we believe, based on some of the other rate projects that we looked at, that it's the decay of uranium to lead. The assumption that rate has been constant, that assumption is subject to question. We believe that there's evidence, strong evidence, that assumption is wrong, is false, is incorrect. And
so the evolutionists say over and over and over again, they have the evidence. They have the evidence for long ages. In a nutshell, why are they wrong?
They're wrong because they assume that the decay rates have always been what we measure them to be in the laboratory at this moment in time. When in reality, there have been episodes in the past when the decay rates have been much, much higher than they are now and ran up.
Okay, so they assume the decay rates are constant, and as a creationist, you have evidence that it was not.
Yeah.
Where's the evidence that it was not?
All right, first it's the fact that it's impossible for the helium to be retained that long in these crystals.
Okay,
that's
the number one.
That's number one. We had several other lines of evidence, independent lines of evidence, that are probably too complex to go into, but a phenomenon known as radio halos.
Yes.
So we had that research as part of the rate project also showed that there'd been a very rapid decay of uranium during when these halos were formed.
Right. And I do want to mention that there's a book.
There's a book
on the rate project. Well, actually, there's two. There's one that's for the general public, and another one that's for
the briefer book.
Even
that's rather technical. It's called Thousands, Not Billions.
Okay, right. And then there's a video with the same name.
Yes, there's a video by the same name. It's somewhat technical also. It's a video of the conference we did at the end of our rate project at a church in San Diego.
Okay.
And it's all the scientists who did this work have about an hour presentation. That's what the video is about.
Right. But the video isn't that long. Yeah, the video itself is maybe an hour long.
Yeah.
Right. But the point is that for those that want to get deeper into this subject, that they can go to these resources
and then there's an 800-page technical report.
Okay.
And that's free, available free online.
Okay.
So if a person is really interested in the technical details, they can get that, or you can pay $50 and buy the hard copy book.
Okay. So in your research and your study with the rest of the rate project and so on, would you say that are you just 100% comfortable that the evolutionist view of the radioisotopes is?
Yes.
You're just that convinced?
Yes.
So thank you for submitting to this interrogation and allowing me to interview you. It's been fun.
It's my pleasure, and basically it's exciting to find this evidence that supports a straightforward reading of the Bible, of God's Word.
It absolutely is, yes. And this is just part of it. I mean, this is just a very small part of the rate project and part of what is going on here at the International Conference on Creationism. So, all right, great. Thank you.